Now that we've found the partial differential equation that is governing the motion of this string, and we're interested in now solving it for w of x of t, what is our next move? How do we actually go from this PDE to w of xt? Well, one thing that works to our advantage because of a lot of the limitations on getting to this partial differential equation is that all of our x terms are going to be only on the left-hand side, and all of our t terms are going to be only on the right-hand side. And that's going to aid us in actually being able to even get to a closed form solution for this particular PDE. So what this lets us do is say that w is separable. If we could not separate the x and the t terms on the left-hand side, the right-hand side, we would not be able to do this, and we would probably need a numerical solution or maybe some other methodology. But what we can say is that our function w, this displacement, we can write as actually the product of two functions. We have w, which is now only a function of x, and we multiply that by t, which is only a function of time. So because it's separable, we can write our solution w this way as the product of actually two one-variable functions. So how does this help us? Well, if we substitute it into that partial differential equation, if we put in w equals capital W times t into this partial differentiation and the right-hand side partial differentiation, we're going to get this out. On the left-hand side, the t term is going to be constant, so it's not going to be affected by the partial differentiation with respect to x. And on the right-hand side, the w is going to be unaffected by the time derivative, so that's going to be able to come out. So I can divide both sides by the w, that's where this w comes from over here, and I can divide both sides by t, and that's where the 1 over t term is going to come over on the right-hand side. And what we see happening is we have this w being differentiated with respect to x, or really twice with respect to x, and this t term being differentiated with respect to t, and they are equal to each other. So because they are being differentiated with respect to two different variables, and they're equal to each other, they must also then be equal to some constant term. And that's where this last right-hand side is going to be coming from. I am saying they're both equal to a constant. It cannot be varying in space or time what these two sides are equal to. So because it's equal to a constant, I am going to, and we'll see where the payoff is for this particular choice of how I name this constant, I am going to call this constant value they are both equal to negative omega squared. I could have called it anything I wanted. I'm using negative omega squared because this omega is going to become important, or an important variable we're going to be finding as we go forward. All right, so admittedly, I did do a little bit of hand waving here. For more of the details, you can go back into your ordinary and partial differential equations book or class and see where this is coming from again, but you should have seen this in your first ODE PDE class. So what this really gives us is two ODEs instead of that one PDE that we started with up here because it was separable. So we have two ODEs now. We have from here the c squared over w d squared w dx squared. I can equate that, I'll ignore this middle section for now, I can equate that to negative omega squared, and I can do some rearranging, and I get my first ordinary differential equation in terms of w. Right? And again, w is only a function of x. I only have constants and x terms in my first ordinary differential equation that comes out from this. Now, if I just look at this section with the t's, big T and little t equal to my negative omega squared, I can take this ordinary differential equation and I can write it by itself. And I get this second ordinary differential equation that has only functions of time in it. So I've gone from a partial differential equation to two ordinary differential equations, one in space and one in time. So what this is going to let me do is somewhat independently, I'm going to be able to solve each of those ODEs. I'm going to start with the spatial one, the one where I have my capital W, and start to work on that. So taking that, and I'll put t aside for right now. This is the ODE I'm working with here. We see it is second order. I have a dw dx squared, and I have a w term. So there is no first derivative here. There is only the second and a 0th derivative term. And we've solved ODEs that looked like this before. This is, now it's in the space domain, not the time domain, but back when we were looking at 1DOF systems, this would look just like an undamped system. So we've seen what the general solution to a second order ordinary differential equation looks like. It's going to be in the form of some constant times a cosine term plus some constant times a sine term. Now here I am going to leave it in terms of a cosine term and a sine term. I'm not going to reduce it to an amplitude and a phase of a cosine. I'll leave these as separate. And we see here this omega squared over c squared. Like we saw previously, that is going to come into here as an argument inside the cosine and the sine. So we have looked at systems that looked basically exactly like this. And now we see why I chose that constant to be that negative omega squared when I could have chosen anything. Well, the nice thing about choosing that negative omega squared is now I have inside here this omega over c multiplied by my x. So that's my first general solution for w that I will be looking at in a little bit more detail in a moment. And now I can look at what does a general solution to my t term look like. Well, here again, it's a second order ordinary differential equation. I don't have the c in this one, I just have that omega. And it is going to have a very similar general solution to it, that t of little t is going to also be a cosine and a sine term. Different amplitudes, I'll call it c and d. And now because I just have this omega squared in front of the t, that's the argument associated with the cosine and the sine term. Now we want to go about getting these constants a, b, c, and d, and actually we're going to be interested in what omega is as well. So we're going to start with this w of x and starting to solve for its constants using some boundary conditions. Because w is a function of a spatial variable, not a time variable, boundary conditions are going to be how we solve for these constant terms. And we are going to only be looking at homogeneous boundary conditions in this course. So the different possibilities we're going to have for strings is we're going to know something about w of 0, w of L, w prime of 0, or w prime of L when we have a string. So that means that we are going to know something about the deflection at x equals 0 or x equals L, or we're going to know something about the slope, which is w prime at x equals 0 or at x equals L. So two of them we're going to know because there are two constants. And an idea we're going to use here is we are going to be finding non-trivial solutions for this w of x. And we'll see in the example how we could easily arrive at a trivial solution. A trivial solution would mean that both the a and the b constant would be 0, which means that no motion would be taking place in our system. And if we have a vibrating string with initial conditions, we know that that cannot be the case. Again, we'll get to more detail in the example problem. Because we want non-trivial solutions for w of x, this omega, or really what's going to turn out to be the natural frequencies of the system, we are going to be able to solve that in order to solve our boundary conditions. And what we're going to be seeing is we're going to, when we have these homogeneous boundary conditions, we're going to be able to get this down to a single constant, an a or a b, but we're actually going to drop it for the next step when we go into the time domain and solve for t. Again, we'll see what that looks like in a bit. So this is what the solutions are going to look like once we apply our boundary conditions. We're going to solve for a or for b. One of them is going to be 0, depending on what the boundary conditions are. And we are going to know our omega n. We're going to know the natural frequencies. We are actually going to get an infinite number of these wn's because we have an infinite number of natural frequencies. So all of them are going to be satisfying our boundary conditions. So Once we solve for our natural frequencies, where we get an equation that expresses them, and we are going to solve for A or B being 0, is typically going to be the case for these homogeneous boundary conditions. These WNs are what we call the eigenfunctions of the system, and they are going to be analogous to what we saw for 2-degree multi-degree of freedom systems when we had mode shapes. So for those multi-degree of freedom systems, we had as many mode shapes as we had degrees of freedom. Here for the eigenfunctions, well, we have an infinite number of them that are going to be associated with each one of our infinite natural frequencies, and those are the eigenfunctions of the system. Now again, with a little bit of hand waving of the mathematical details of what's happening here, because there's an infinite number of these are actually going to look like a Fourier series because there's an infinite number of these eigenfunctions that satisfy our boundary conditions, and we have to account for all of them. So we're actually going to superimpose all of these natural frequencies and mode shapes or eigenfunctions as a Fourier series. So starting to put this together a little bit more, we have these Wn eigenfunctions, and we're going to sum up an infinite number of them, and that is now looking like our W function. So remember, it was separable, so it was W of xt equals big W times big T. Big T we haven't gotten to yet, but big W we are now expressing as this infinite series of eigenfunctions. So once we have the eigenfunctions, the next step is going to be addressing big T, this cosine of t term and sine of t term that we have here. So now we can go into the time domain and start to do some analysis. Since we're in the time domain and we are trying to solve this ordinary differential equation, we are going to need to apply initial conditions. So what is happening to our string at time equals 0? That is going to lead us to be able to find the Cn and Dn coefficients, of which there will be an infinite number of them. So what we're interested in is we need to find what is the initial position of our string at time equals 0. So W of x comma 0. We're setting t to 0, but we need to define what is the position at all points in space at time equals 0. And our other initial condition will be on the velocity. What is the initial velocity of the string at all points x when time is equal to 0? So the initial positions will give us what the Cn value is, and the initial velocities will tell us what the Dn value is. So we're going to be using the eigenfunction that we just came up with in the previous step from our boundary conditions, and potentially we're going to be using those natural frequencies as well when we are doing our velocity calculation. So to get from our initial conditions on position and velocity to the actual coefficients, all infinite of them, we are going to take a step or a method that looks very similar to what we did when we were working out Fourier series expansions early on. So the Cn term, we are going to be able to find that by doing this calculation here, the 2 over L times the integral from across the length of our initial positions times our eigenfunction. And we can complete that integral, and that will be a function of n typically, and that will give us those C sub n coefficients that go into our equation. Then we're going to do something pretty similar. We're going to take those initial velocity function, multiply it by our eigenfunction, and then integrate that, and then multiply it by 2 over our the nth natural frequency times L, and that gives us those Dn coefficients. What we want to be careful of when we're doing these integrals is remembering that this W is a function, little w is a function, our initial positions are a function, as are the eigenfunctions. These are going to contain n terms. Same thing down here, this W dot is a function, and W of x is a function, and it contains n terms. And in addition to, we're dividing by the nth natural frequency to find that nth D coefficient. So once again, these are the general steps we take. It will become clearer when you look at the specific example in the next part. of calculating these Cn terms and this Dn terms. So what do we do from here? We'll have Cn defined, we'll have our Dn defined, and what we can do is actually go back. Once we know the Cn and the Dn, we can plug those in to this equation, and we're going to be able to put it all together, and this infinite series is exactly equal to now our w of xt. We're going to see the right-hand side has t functions from this cosine and sine, and our wn here is our functions of x. So for any point in space x at any time t, we are going to know the deflection or the vertical position of the string at that point x in space along the length of the string and that point t time after 0. So as a quick summary of what turns out to be typically a lot of steps to go through when we are dealing with a string. The first thing is we need to identify our system as a string. Is it a system where we have only that internal normal force and we don't have internal shear forces or internal bending moments? And furthermore, to use the equations as we did, we had to make sure that those limitations were in place. Is it a string with constant tension, with a constant density? Is it autonomous? And does it have small angles? All of those needed to be in place so that we got that particular PDE that described the behavior of the string. And we need it to be that way because that particular PDE we're working with is going to be separable. So we're going to separate it. We can say that our solution is going to be this capital W times this capital T. Then we can go and work on W. So we need to identify our two boundary conditions. Where on the string do we know the deflection and or the slope? Now, typically for a string, we are going to know that the deflection at the endpoints are 0. And that's going to almost always be the case in string-like elements or string-like systems. And this will be different than if we have a column, which we'll be talking about next. But what are those two boundary conditions? We're going to use one of those boundary conditions to find that either A or B is 0 in the string, in that w of x equation. But we cannot say that both A and B are 0 or we get that trivial solution. So we're going to see that the other boundary condition is going to be used to find the natural frequencies of the string. Once we have the natural frequencies, once we have one of those coefficients equal to 0, then we can write our eigenfunction. We can find what w of x is, or really w sub n of x, because it's a function of the nth natural frequency. We have our eigenfunction, then we can go on and apply our initial conditions to find the coefficients for the capital T term, those Cn terms and those Dn terms. Right, so we use those by doing integrals. We use our initial condition on the vertical position of the string, and we use the integral using the initial velocity at every point along the string. And that will give us the C's and the D's. We put those all together with the eigenfunction that we found previously, and that is how we get our w of xt as an infinite sum of our eigenfunctions, those coefficients C and D, our natural frequencies, and we're going to see the right-hand side is a function of x and of t. So written here as a summary, it looks like it's not that much, but every one of these steps we're going to see in the example can take a decent amount of work to get to our closed form total solution that is going to be that infinite series.